Hello, so today we are going to take a look at this problem called minimize the difference between target and chosen elements. So what the problem says is we have a m by n integer matrix and we have a target value. And we want to choose one integer from each row in the matrix such that the absolute difference between target and the sum of those chosen elements is minimized. So we want to pick essentially one cell from each row and then take the sum and then take the difference of that with target, the absolute difference of that with target, and we want that value to be minimized. What we are free to use here is whichever value in each row we want. And so an example here is this first example. We have this matrix, right? And then we have target value 13, right? So the best absolute difference, which means the smallest absolute difference we can make here, is taking 1 from the first row, 5 from the second row, 7 from the third row. So that would be 6 plus 7, that's 13, minus 13 equal to 0. And what we want to return is the minimum absolute difference value. So 13 minus 13, that's 0. So we choose 1 from the first row, 5 from the second row, 7 from the last one. For this one, it's kind of easy because we have only one choice. So we have to pick 1, 2, 3. So that's 100 minus 6, that's 94, right? For this one, we have only one row. So we get to pick whichever one will minimize the difference. And so target is equal to 6. So what minimizes the difference is 7, right? 7 minus 6, that's 1. The absolute difference is 1, so that's what we will return. So this is the problem that we are trying to solve. And so, yeah, let's get started. Okay, so how can we solve this problem? So two important things that were in the constraint of the problem are that the number of rows and the number of columns can be each at most 70, and the values in the cells can be at most 70 as well, right? And so that kind of gives us an idea of how can we solve this. So what this would mean is that the sum itself, so remember the goal here is to, so the goal of the problem is to minimize absolute diff with target. And basically with target and with the diff here, we are the sum of chosen elements from each row, right? So these are kind of the goals of the problem. Now, can we say something about this sum from this constraint? Yes. So the sum would be, so we are picking one element from each row. That means it's at least 17 numbers, right? That's because we can have at most 17 rows and we can have at most 17 columns, right? But from each row we are picking just one, so at most we have 17 numbers, right? And then each row, each value we pick, right? Each element value is at most 17, right? So what this tells us essentially is that, well, sum itself is at most the sum of 17 numbers, and each of them is at most 17, right? So it's at most 17 to the power of 2, right? So what this tells us is, okay, this is not actually very big. Like if we iterate over all possible, if we do a brute force and iterate over everything and keep the sums, the intermediary sums, so what this would mean here is if I had something like this, right? And then I have rows. So let's say this is position I, right? So in position I can keep a set or a list of all the sums so far, all sums so far. What I mean by all sums so far is, let's say, the sum of picking the first element from the first row, the first element from the second, and then like this. And the other sum would be picking the first, and then picking the second, and then picking the rest. So all the combination basically of the positions, we can put them in S, right? And so let's try that with just a brute force solution and see what we get to. And so we'll just write it, and then from there we can see if the complexity is very high, we can optimize it, okay? So the function would be minimize difference, and we will get a matrix and the target value, okay? And so what we can do here basically, let me write that. So what we can do, want to keep track of all intermediary sums, right? So here we would keep track of the sum for each value alone, right? Just the value alone. And then when we get to the second row, we'll pick this and this as a sum, and then this and this as another sum value. So we'll have S contains all intermediary sums so far, right? And so initially, just before starting, we need to have some value that we can add just to start from. So let's just have 0, right? That doesn't change anything. So we can just have 0. The sum doesn't change anything. And then we'll go through each row in the matrix. Okay, what should we do there? So what we want is to pick each cell and add it as a new sum. So what would this mean is 0 for row 0, right? Let's say we have maybe we have this here. Let's take an example. Actually, this would be easier with an example. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we are here at the first row. So what we want, and then we have just S is equal to this. So what we want is to add to the 0, 1, put that in a sum, because in each row we can pick only one cell. Then take 2, and then take 3. So each one of them. So what this would mean is our S would be, so notice here I added it as a set. This is to not have duplicate elements, because if we add an element, a value to the same number, right, it's just the same, so no need to add multiple times. Let's just keep always unique sums, right? So what this will mean, let's add 0 to 1, right? Let's add 0 to 2, that's another sum, and let's add 0 to 3. So this is the sums so far, basically at row 0, okay? And then the next iteration with this for loop, we'll go to the second row here, and we will go with this S. So that would mean we will take 4 and add it to each one of them, right? So our S would be 4 plus 1, that's 5. 4 plus 2, that's 6. 4 plus 3, that's 7. And now we did 4, we are done with 4, we go to 5. So what this would mean is 5 plus 1, that's 6, we already have that. Since this is a set, it's added only once. 2 plus 5, that's 7, we already have 7, so we don't need to handle it. And then 3 plus 5, that's 8, that's a new number, so let's add it. Okay, now we are done with 5, and let's go to 6. Okay, so 6, let's add 1 plus 6. So we add each cell from the row to each sum, because that will get us the different combinations, right? And so 6 plus 1, that's 7, we already have 7. 6 plus 2, that's 8, we already have 8. 6 plus 3 here, that's 9, we don't have 9 yet, so we add it, right? And then we keep doing this, we do the same thing for the last one. Okay, so how can we do this here in the Leetcode? So basically what we are doing is just finding all the possible sums by picking each possible each cell from a row, each different cell from a row, and having all these possible sums in a set. And so what this would mean here is that, well, our S each time just becomes S plus A for X in row, sorry, for A in row, so, and then for S in S. What we did here is each time we picked a value in the row, we added it to a value in the sum, and that's exactly what we are doing here. You can think of this as doing two loops essentially, right? One over the row values and one over the sum values. That's exactly what we need to do here. And we keep them in a set. And then at the end we need to return. We look at all the possible sums that we gathered so far. So this is just brute force, right? And we need to return the min of the absolute value of target minus X for, okay, let's see, let's keep the notation of S, lowercase s here, for S in S, right? So we just take the min difference for all this between all the sums. I realize this one here may be a little bit harder to understand, like just this way of writing it in Python, so let me just clarify that a little bit. So this is just equivalent to saying, let's create a new set, right? And then let's do a for loop. So for every row value and for every sum, let's just add to ns s plus a. And then at the end, we will do s equal to ns. Override, right? So this is very, very much the same. Okay. Now, what is the time complexity of this solution here? And is it good enough? Okay, so we know that we are doing all the rows first. So this is O of M. M and N are at most 17. So let's just kind of use N as the value. In terms of complexity, it doesn't really matter a lot, so that we can get a nicer written complexity here. So what this would mean is here we have O of N, and here this is O of N. Now what's S, right? So S, we said here, can be at most this. So S itself is at most the length, its length, how many elements are in it, as we said here, is at most O of N squared, 17 to the power of 2. So since these as nest are nested like we saw with this, we need to multiply them. So the time complexity overall for us is O of N to the power of 4, right? And this is a really big number, right? So yeah, I suppose it's likely we'll get TLE. So let's think about how we can improve it. How we can improve this brute force. So there is one observation that we can make, right? Which is, for a matrix here, if we take the smallest value in each row and sum it up, that will give us the smallest possible sum, right? So we can take the smallest sum, right? That would be just the sum of the minimum of each row, right? For each row in the matrix. And if the smallest sum is bigger than the target, what does this mean? That means that if we try other sums in the matrix, those will be larger than smallest sum, right? So by definition, smallest sum is smaller than every other sum in the matrix, right? And so we won't improve on the difference, right? Because if we do this minus target and this minus target, this would be smaller, right? So we immediately know if the smallest sum is bigger than the target that this is the best we can do. So we should just return it right away. So just return smallest minus target, since smallest is the bigger value, right? Okay, so this is kind of one optimization we can do from the start. Doing it from the start is good because that will cut some things, but it's not enough because the bulk of our work is actually here in these loops here. So how can we take advantage of this also in our for loops? Let's draw it out and see what happens. So we start out the sums. We know that all the values are positive, right? That's what the constraint tells us. And so we know that our sum at least is 0. And somewhere here we have target. Somewhere here we have target, right? And then somewhere here we have 2 multiplied by target. This is just like, you can think of it as a kind of axis for the values. And we have 2 cases, right? For the smallest sum, right? The smallest sum is either here, somewhere here in this region here, if it's smaller than target, or if it's bigger than target, it's somewhere here. For smallest sum bigger than target, we already handled that, we already returned it, so we don't need to think about it right now. We need to think about only the case where it's smaller than target. So this is the remaining case. So this is our remaining case that we need to think of, okay? And so if our smallest value is somewhere here, right, let's say maybe just for the sake of demonstration, let's say it's somewhere here, smallest. So this is equivalent to this value here. So the smallest sum, okay? What is this distance here? What is this distance? Let's call it A. So, or let's call it maybe just for the sake of, let's call it D1. What is D1 actually? D1 is just the value target minus the value smallest sum, right? So it's just target minus smallest sum. Now, one thing we can, one observation we can make here is, let's just add smallest sum to target. If we just add smallest sum to target and get a value B here, so let's just suppose B is equal to target plus smallest sum. So it's kind of just like a projection of it here. So this is a D1 as well. We know that any value, any sum in this region here, so any sum in, let's say, let me pick something. So any sum here, sums here, we can discard, right? We don't need to look at them. Why is that? Because we can already do better, right? We know target minus, because any sum here, so any sum, any S in B to target, right? The diff would be bigger than D1, right? It would be something like this, bigger than D1. Is bigger than D1, and D1 is already what we achieve with the smallest sum, so we don't need to look at it because we know we already have a better one with the min. So how can we, so we can take advantage of that, right? And just discard all of these. When we have a sum like in these, we don't need to continue keeping it in our S here because it will only get bigger, and so it will not be useful for us. It will never be a solution, so we can discard it. So the result from this observation is that are not useful. So just prune them. This is what's called prune them, which means don't look at them, remove them from the set that you will explore later. So prune them. That's what we'll do here. Okay. So how can we do that? So that means that what are these S values that are between this? So these S, basically, these sums are smaller, are bigger than this here, than B, okay? And so what that means is that this S here, these sums here are bigger than target plus D1, right? Are bigger than target plus D1. So actually this is what I should have done here. This is target plus D1. And so what's D1? So this is just target plus target minus smallest sum, which is just equal to 2 target minus smallest sum. So I went into like a detailed breakdown to really make sure you understand it, but intuitively you can just visualize that, okay, it's target, it's after target, but after target by just target minus smallest sum, right? And so you add to target minus smallest sum, you get 2 target minus smallest sum, right? So that's pretty easy. So what this would mean is that we can just discard in this S, we can discard those that have this property and just keep those that are smaller or equal, right? So let me modify then my this algorithm here to do that. So okay, let's just copy it and keep it for our own viewing. Okay, so I'll just put this one here. Okay, so this is our initial solution that we are going to prune, and let's start our new solution here. And so we'll take M and target. Okay, so yeah, these ones stay the same. S is still equal to 0, and then we still need to go through row. And then we do S is equal to same thing that we had for A in row, for S in S. But we take this value only if we know it will work. So only if it's not bigger than target plus D1, only if it's not bigger than this, which means only if it's smaller or equal than that value. Sorry, I forgot to do one thing here. Let me do it again. Let me put this here. What we need is to do the initial pruning that we did here. So that would be, we pick this, right? Copy. We add it here in the beginning. We don't need to do any loops if this is true. So we take the minimum, the smallest sum, which is just the minimum for each row. And if it's bigger than target, then we know we can do better than smallest sum. And so we just take that as the absolute difference. And then we just take a look at this one. So we pick the sum only if it's so here we pick the sum, which is S plus A, only if it's smaller or equal to 2 target minus smallest sum, because if it's bigger, we already can do better with smallest sum, right? So we do smallest or equal to 2 target minus smallest sum. And this would be the end of our set. This would be our set. And then at the end, we do the same thing we did here, which is just return the min. And so we just return the min of the absolute difference of target minus S for S in the overall set that we calculated. And with this, we will remove a lot of things and not need to explore them. And so let's write this down and make sure it passes test cases. But this is the main idea here. Okay, so let's type our solution, our improved solution, and make sure it passes test cases here. Okay, so what we said we need to do is we need S, right? Start out with 0, and we need to compute the smallest sum. So that would be equal to just the min of the sum of all the minimums of row. And then we need to grab as well we need to check if that smallest sum is bigger than target, then we are done. Can do better. And so we'll just return it. Otherwise, we just do our for loop. And this is big S actually. And we don't need to initialize it until here. And then we say S, we override with S plus A for A in row. And then for S in S. And then only if S plus A is smaller or equal than 2 times target, the value that we deduced from our observation, smallest sum. And then at the end, we just need to return the minimum that achieves the absolute minimum difference. So that would be the minimum of the difference of target S, and for S, we go through all possible sums. Okay, and that should be it. So let's run that. So we want to grab the sum for, yeah, M. Just name that one. Okay, let's test with all test cases. Let's submit. Okay, yeah, so it passes test cases. Yeah.